actual recording, so we are now live. So yesterday we talked about, let me just go here. You're seeing, I hope you're seeing this, these slides now. So we talked about yesterday about the KKT conditions, the Karush-Kuhn and Tucker conditions, which was expressed as theorem 5.2. I tried to explain it in such a way that the idea here is that this part which deals with the gradients of G and H are basically there to give you information about the directions into which you can move from the current point. Let's say we are at X star, and delta, sorry, not delta, this gradient of F is then the direction into which F will grow. And the intuitive meaning of the Karush-Kuhn-Tucker conditions is that the function will grow into any such direction that you are allowed to move without violating the constraints. That's what it says. If you can move from this point to somewhere else, then the dot product with respect to that direction and the gradient of F will be positive. That's the main idea here. And we developed the theory a little bit here, talked about certain situations, had an example here, example there. Very common situation, like in the example 5.8, is that we have certain conditions and we transform these conditions into the KKT conditions as per the theorem 5.2. And then we find all the solutions that satisfy this. And there are these parameters, for instance, in these inequality constraints, the coefficient for the respective inequality constraints gradient is going to be a positive coefficient, because it means that, you know, we have here the barrier, we have the gradient of the G function. G is 0 here, then F must increase in only when F must increase in this direction inside the territory, so that the decreased directions are all towards the outside region, and so forth. So the coefficient there must be positive, and so forth. So we come up with all these possible situations. All the coefficients are 0. This is what we call an internal point, right? I mean, none of the constraints are active. And then one by one, we try different combinations of which of these inequality constraints are active. This example dealt with the inequality constraints. Those are relatively simple situations. And of course, if we have both inequality and equality constraints, we have to list out all those possible combinations when we deal with the KKT conditions. Usually we don't do that. We do something a little bit else, and then only check later whether the points we found are actually KKT points. And I mentioned that there is a situation such as this. I call this the bird's peak form. So when we have a situation where, in this case, it's the situation where the gradient of the constraint function reaches 0 here at the peak, then that's a situation we have to look at separately. It doesn't satisfy the KKT conditions, but because the gradients, remember, one of the quality constraints was, constraint qualifications was that the gradients of the active constraints must be linearly independent. The equality constraint is always active, and if it has a gradient 0, then no matter what kind of collection of gradients we have, if it has a 0 vector in it, it's not going to be linearly independent. And that's a situation where we have to double check. So be mindful of that. The constraints, if the constraints, constraint functions have zeros of the gradient, then it is possible that those points might be optimum points, even though they don't satisfy the KKT conditions. That's the important thing to take away from this example 5.9. Well, now let's move to a situation where we only deal with equality constraints. This is something called the Lagrangian method. I mean, those of you who are familiar with it will know what I'm talking about. Usually we teach this in earlier courses, but this situation, we can think of this as a special case of the KKT condition. So if you know how to use the Lagrange method of optimization, then good. If you don't, then this is another opportunity for you to learn. So very often the case is such that we have a trajectory of some object that is defined by some equation. Let me just draw just a second. Let me draw a picture for you. So for instance, we have here some point X, and then here's a curve. And so let's say that we have here some point, and there's a curve here, and we need to find out which point is the one that is closest to this. So this is defined by some h of x equals 0, this curve. Here, the distance from this point is determined by, we want to minimize it. Let's say that's the minimum point. So it will be a KKT point. So there's a function that tells you the distance of each of these points, from this point, and it's going to be a simple quadratic function, obviously, or we can take the square root of that, but the distance, it doesn't matter whether we minimize the square of the distance or the distance itself, really, because distance is distance. It's an increasing function. So if we do this and we deal only with equality constraints, then this is what we get. And we express the KKT conditions as follows. So the gradient of the cost function plus a linear combination of the gradients of the equality constraints, they must amount to 0. So, and of course, the constraints h of x must all be equal to 0. So if we express this in vector format, so we take the gradient of f plus the Jacobian of the h, that would be a vector, times some vector delta, lambda, then that should be equal to 0. So what we're going to be having here is basically a linear equation here. So now instead of looking for the solution of simply finding the x, we increase the dimensionality of this problem into finding the x and then the lambda, both at the same time. So if this is easier for you to think in terms of just, let's say it's just two-dimensional, then you can think of a trajectory, let's say a parabola. You can think of it this way. A special case that is easy to solve from this is to think of a parabola, and let's say that f of x is equal to the distance from some particular point. And now my x is a two-dimensional vector, so my h of x is actually h of x and y, and the h of x is, in this case, is x squared minus y, because then we are the points that are admissible is where y is equal to x squared. So the points on a parabola. And let's say we have some point somewhere else, let's call that AB, and we can calculate the distance at each point is then x minus a squared plus a y minus b squared. That's the distance from the point AB. And you can do this with pen and paper concurrently if you want. I mean, if it makes it helpful. And in this case, we would be finding a solution to, we increase the dimensionality by 1, because we're going to be looking for a lambda coefficient for this h of x function. So we are going to be looking for x, y, and lambda, and we're going to call this new vector z. Of course, I mean, how many components there are in this lambda depends on how many of these constraint functions h there are. So if there are p of these constraint functions, then this new vector has dimension n plus p. In my example, it's 3, so we have x, y, and lambda. And we call this the Lagrange function, and the Lagrange function is simply defined as f of x plus lambda times h of x. And where this, if this is a vector, then it's lambda transpose h of x. And if we solve this, we can generate we can calculate this is now one function of several variables, and it's got a scalar value. So it's a real valued function of dimensionality n plus p. So it's from Rn plus p to real numbers. And this is minimized when the gradient of the Lagrange function is 0. So we're minimizing this. Okay. To minimize this, we set the gradient of Lz, this new, to 0. So it means that the gradient of this L with respect to those components that pertain to x, and then both the gradient of L pertaining to those components that relate to lambda, that vector as a whole is 0. So we can now solve this fairly easily with just univariate, not univariate, unconstrained optimization algorithms. For instance, we can do this with the Newton method, for example. So we've now transformed this problem into a one-dimensional problem. It's not one-dimensional. Sorry, not. I always could. Sorry, not one-dimensional. To unconstrained problem. So let's see. We would probably want to express this in terms of the KKT conditions. But if we rewrite this out, I mean, if we write this out, setting this gradient of L to 0, then what does it amount to really? I mean, what is the gradient of that? Well, if you calculate the gradient of this pertaining to Lz pertaining to x, that's simply the gradient of f. And if we calculate the gradient of this Lz pertaining to this delta, well, it's simply this multiplication. So it's going to be just delta times the derivative of h. So it'll be just this h prime transpose delta. So we're actually, when we get this gradient of the Lagrangian to 0, we're actually, that's a KKT point. And we can use the Newton method on this by just simply doing the Newton method, that as thinking this as just one unconstrained problem. The problem is, of course, that we may get a local maximum or a saddle point or so forth. I mean, depending on the same drawbacks that Newton method has. If we start with a point that's too far from the optimum, or we end up in a region where the Hessian of the Lagrange function is going to be not positive definite. If it's not positive definite, we may run into problems and so forth. But really, I mean, those problems we've already talked about how to solve those, how to figure those. We can use the modified Newton's method, or we can use the quasi-Newton method or something like this, which we saw that they help us enormously to find the optimum in this case. So here, if we do this with the Newton method, we notice that first and foremost, if we calculate if we calculate the Hessian of the Lagrange function, then in the upper left corner, we simply have the X components, the components with respect to the actual variables X. In the upper right corner, we have the Jacobian of the constraint functions, and similarly in the lower left corner. Of course, the other one is transpose. This is symmetric. And in the bottom right, we have zeros only. Why is it zeros only? Well, think about it this way. The part that talks about the constraints, we've already, if we take the derivative with respect to X, then that eliminates the lambda. And if we take the derivative with respect to lambda, that eliminates the X. So it's just going to be zeros there. So, sorry, no, sorry, I misspoke there. So this is the part where we eliminate the lambda by taking the derivative with respect to lambda. That eliminates the lambda. With respect to X, we get the H prime of X. Here we get lambda is taken out first, and then the derivative with respect to X. But in here, we take the second derivative with respect to the lambda coefficient. But the lambdas only appear as linear terms. So if we take lambda 1 first time derivative, the lambda is eliminated. Second derivative with respect to lambda 1, you know, it's 0. So that's why it's, sorry, I misspoke there. And then rewriting this in terms of the Lagrange function and this Newton method step, we get this equation which gives us the solution to this step. So in essence, we can solve this, we can often solve this explicitly. Does not need to go here in great detail. We just call this, notice here we mark this with JK because it's called the Jacobian. When we have vector valued vector function and we have the derivatives or the gradients with respect to each component, so we have several gradients, they form a matrix, so that's called the Jacobian matrix. Here's some linear algebra. I don't see there's a lot value to be gained. You can look at this, how this block matrix representation gives us. So we can calculate what is called the Schur complement of this A11, and we get this inverse of A. I don't see much value in here because, you know, you do this numerically anyway most of the time. If you run into trouble there, you know, you can consult the theory and see what's going to go wrong. I'm not going to spend time on this part here. So let's take an example. So we're minimizing a quadratic function, x squared minus x1 squared minus 4x1 x2 minus x2 squared, subject to x1 squared plus x2 squared equals 1. So basically we are talking about the quadratic function that seems to be negative, have only negative coefficients, under the constraint that we are talking about the unit circle, the points on the unit circle. We can write this in matrix format. So for instance, you can write this first, this is a quadratic function, so we can write this in a quadratic form. So it's going to be this minus 1/2 times x transpose A, where A is the matrix 2, 4, 4, 2. You can double check. And also this h of x, well, this is the norm of the vector x. So we can write it as norm of vector x squared minus 1 equals 0. So this is a quadratic function whose minimum is to be found on the unit circle. We can express these KKT conditions as follows in vector format. Well, there's only one lambda there, and the h of x must be 0. Now, if we, sorry, this is a little bit unreliable. Let me just zoom in a little bit. So we have here the situation that the gradient is simply minus ax, and the gradient of h of x is 2x, so we can get this into the format that a minus ax squared plus 2 lambda x equals 0. So this becomes what? Only the eigenvalue problem and eigenvector problem of a particular matrix. And we can solve this explicitly. So this is an example where we can solve it explicitly. We can do it with the Newton's method, and we can find certain solutions. You can try this out. I mean, if you want to try this out, you can try it out with the method that we did. We'll do this in the exercises this week, but I just wanted to show it here. So here's a picture of it. So there will be 4 points corresponding to the KKT points, and then we need to figure out which of these points are actual minimums and which are maximums. The reason is, in this picture, you know, this quadratic function, those contours are written here. The contours are, a contour of a function is simply the line along which the function's value is constant. So these points are in fact points where the contour line is parallel, the point where the exact contour line is parallel to the circle's arc. Those are the KKT points. I mean, the graphical interpretation is that those are the KKT points. And the question is, which ones are minimums and which ones are maximums? Well, you can try what the number is in different points here. The thing is, in this case, when we do formulate the Lagrangian, then the algorithm doesn't progress by, you know, moving along this this edge line and then converging to that. Instead, it moves somewhere else. You can start from the inside, and then the Newton method makes it move from point to point and get converged to the, well, depending on how it's defined, not necessarily the nearest, but the one where it's the easiest to get to these KKT points. So you see, this is an example of a case where the solution is relatively simple, but it's where you end up is sensitive to the selection of the initial point. We'll see that, we'll explore that. And that the function may get somewhat different values. So for instance, if we start at -1, 1, and 0, we end up at a point where the function's value is 1. But if you start with 1, 1, and 0, you know, x, y, and lambda respectively, then we end up at a point where the function has value -3. So it's smaller than that. So one of them is the global minimum and one is not. Okay, so the Lagrange method is basically a method by which, by increasing the dimensionality of the problem, we transform it into a unconstrained problem, and then we can just go ahead and solve the problem with the methods that we learned in the previous chapter. So equality constraints in this sense can be thought, I mean, as long as we're dealing with continuously differentiable functions, then you can think of the equality constraints as being relatively easy to tackle. Let's take a little break here. Not a break, really. I'm not going to give you a break here. I'm going to divide you into these groups. There was a chat message here. Nasser pointed out that there is nabla underscore delta. Where is this nabla delta? Is there somewhere in delta? Sorry, I didn't notice the chat. Oh, is it, you mean lambda? Yeah, lambda. Yeah, it's the derivative with respect to the lambda components. You were talking about this this here, right? This is the one you mentioned here in the chat. So this here, you take so the lambda is, in general, the lambda is a vector. In our example, it is a scalar, or you can think of it as one-dimensional vector. I mean, think of this h, it's a vector function. So x is a vector, but h, you can have one h, or you can have several h. And the dimension of the h, I mean, it's a vector of the dimension that corresponds to how many equality constraints you have. You may have 1, 2, 3, 4, any number, right? And the lambda is a vector whose dimension is the number of equality constraints. In most of our examples, the number of equality constraints is usually just one, because we are dealing with usually two-dimensional problems. If we have more equality constraints, then there will be usually just 1 or 2 points that are feasible, because those are the intersection points of intersecting curves. But in general, lambda is a vector. Does this answer the question? Yeah, good. So I'm going to divide you guys into rooms, and I'd like you guys to go transform this example 5.11, not according to this, but calculate the Lagrangian, not the KKT conditions. Calculate the Lagrangian of this. So you have this equality constraint. Calculate the Lagrangian, transform it into the suitable function in MATLAB, and use the Newton method there. So you should get these results in page 124. This is a relatively simple function. Minimization of this function, subject to that. Do a little bit of pen and paper if you need. I'm going to put you into 2 rooms. Use the 3rd week example MATLAB code, but after you've figured out what the Lagrangian is, and calculate the minimum of the Lagrangian and interpret the result. Don't try to draw a picture, because in the Lagrangian you will now have x1, x2, and you will have also the lambda. You can use xy and lambda, or xy and L, or something like this. But try to see if you can do it. And I'm going to now open the rooms. I'm going to give you 15 minutes to do that. After 10 minutes, I'm going to come and visit your rooms and see how you're doing. All right? Formulate the Lagrangian of the example 5.11. So it involves some pen and paper work, and then move to MATLAB once you've figured out what the Lagrangian is. All right? I'll get back to you in about 10 minutes, and I'll come and visit your rooms. Now I am recording. Yeah. So before we get to this, so we're going to be having to change this, and we're going to be needing. I'm just going to call it Z. That's going to be the lambda here. So I'm going to call it Z here, Z, Z, and then I'm going to put here X3, X3, and X3. So it's going to have 3 dimensions. Before I get there, I mean, I had this function that I had. It was given as just going to do the same thing here. X, Y, Z. I could define them as real, just so that we have quadratic forms. That sometimes we want to avoid the situation where it gives them complex numbers. That's not usually necessary, but I just want to do it. So we had this f, which was just basically defined as minus x squared minus 4 times x1 times x2 minus x squared. So I'm going to use x and y, x times y minus y squared. That was our f. And then we had this h, which was basically given as we had that x1 squared plus x2 squared is equal to 1. So we want to write it as h of x equal to 0. So our h would be x squared plus y squared minus 1, because this is what needs to be 0, right? And if we are going to then formulate the Lagrange function, and that's really what we need to do, we're going to be formulating the Lagrange function. So that would be L of x, y, and z. So that would be f of x, y times, not times, plus, then we have lambda times h of x. So we would have this lambda is now in the place that I used z times h of x, y. Sorry, I would probably need to write it like this. So we have here this. This is now our new. This is now our Lagrangian. So I'm just going to punch it in here. So what we are going to be looking for is the 0 of the gradient of the Lagrangian. Really, that's what we're going to be looking for. And I'm going to dispense with the drawing of this stuff, because I'm not. I can't draw that because we have 3-dimensional problems here. I could separate this into 2, but I'm going to dispense with the graphical representation. So we're going to be looking for the zeros of the gradient. And really, we're going to be running the Newton method on this. We're going to be running the Newton method. So I'm going to evaluate this current section here. I have calculated the Hessian and all that. And now you see, as per the example, that the 0 is at the bottom here. And this part here is this part here is the gradient with respect to z. I mean, it's with respect to x, z, and y. Sorry, here, this g of s. So then the gradient, we have the derivative with respect to x, y, and z. Now, let's go to there was a gradient method. So let's solve this with the Newton method. And we noticed that there were different starting points. So I'm going to just have the starting points as, I'm going to dispense with this. Well, we can do it with this. So our xk, I mean, initial guess, I mean, there was just start with -1, 1, 0. I'm going to have to, the draw line I'm going to have to skip, because that I cannot obviously do. And I'm going to run this and see what happens. and I'm going to be running here, the answer will be 1. And the point that we will be looking at is this. It converges to minus 0.7071007 and so forth, and minus 1. So it corresponds to the first question in our first point as per explaining there in the slides. I'm going to now try the 1 point as a starting point. And we see now that there are points, it converges to this one where the first one is no longer minus something, that's 3. And the answer, the value of the function at that point is minus 3. I can try it from different points. I can try it from the origin. This may lead us into trouble. If we look at this, symbolic gradient, if we start from 0, well, it's not going to be 0 there actually because of this. So if we start from the origin, I don't know where it's going to lead us. Yeah, the matrix is singular or close to being singular. It's probably HF if we calculate the Hessian. So what was that? It was given as HFS. So the Hessian is HFS, it looks like that. And if we calculate the HF at 0, 0, 0, then it's singular. So it's singular, we can't calculate the inverse of it, right? So we have to make sure that the starting point is such that the Hessian is not singular, right? And by the way, this is also negative definite. So we put 1 here. Oh, that's even worse. So we need to put something here to make sure that this doesn't seem to be all that. Oh, this is still singular. So we will have to try out points at which the Hessian is not singular and so forth, because we run into trouble with the Newton method. We can try. I'm not going to do it now, but we can try to use the modified Newton method, for instance. It doesn't really matter which we are if we just minimize the Lagrangian here and find a minimum point, then we should end up in one of those points where there's a local minimum of the Lagrangian. And if so, then that should be a KKT point. Of course, obviously, we have to double check later. Is it actually a KKT point? But it's fairly easy to solve and it's fairly easy to check whether it is. If the gradient of the Lagrangian is 0, then obviously it satisfies the KKT conditions. It may well be that the h of x is not equal to 0 at that point. It's possible, and but we have to double check that. Now, do you guys understand what I meant with this exercise? I knew, of course, what to do here, so I could do this in 5 minutes, but, would you be able to replicate this? What do you think? Well, I hope you would. All right, let's move along. So that's what this meant. I'll go through these examples, and we'll do these examples in the exercises as well. So most of the methods that we talk about in the theoretical part in the slides, we can do them with MATLAB. The part of the thing that I want to teach you guys in this course is how to move from the theory to the practice. And I hope that this MATLAB exercise here gives you a way of moving from theory to practice. I'll put some exercises and the extra exercises there later. But the Lagrangian method is fairly simple. We just transform the problem into a higher dimension problem, and then it's an unconstrained problem, which we minimize using whatever method that we have at our disposal, be it Newton method, be it modified Newton method, gradient descent, whatever. We should find the 0 of the gradient there, the 0 of the gradient of the Lagrangian. All right, moving on to inequality constraints. So in this section 5.2, we consider the problems in which the minimized function is minimized subject to only inequality constraints. And when we're dealing with only inequality constraints, then we're kind of already have an unconstrained problem as long as all the inequality constraints are satisfied. The only problem is if our algorithm ventures beyond the boundary of our region. So let me just draw a picture here. Again, sorry, it's two-dimensional. I haven't practiced my four-dimensional drawing skills very well. Plus, I don't have my five-dimensional camera here. Haha. So let's say that this is our feasible region, and for argument's sake, let's say that there's just one g of x, which has to be smaller than or equal to 0. On this line here, it's smaller than or it's equal to 0, and beyond this line here on the outside, it's greater than or equal to 0. And the line marks the edge of our boundary, our condition. So as long as our algorithm is somewhere in here, let's say it's over there, and let's say we're doing something like an unconstrained optimization problem. We are at that point, and we find a search direction, we go in that direction, just like in any of the algorithms, be it Newton method, quasi-Newton modified, gradient descent, whatever. We take one point, we choose a direction, we go in that direction until we find another point. Let's say we go over there. Like so, we move from that point to there. Nothing happens there. The constraint has no effect on what we're doing, and we don't have any trouble with that constraint. The only problem comes if we try to do this, right? If we try to do this, then we shouldn't do this. Obviously, we shouldn't do this, because if it looks like a promising direction, but we end up here, we end up taking it one step too far, then we're violating the constraints, and we no longer have a feasible point. So we shouldn't even consider this point. We should consider some point inside here. So next, we will talk about strategies of what to do here. There are other strategies than the ones that I discuss here. Later, I will explain what is known as the cutting plane method, but that comes at the later stage. In here, we look at two methods: the barrier method and then the penalty method. I'll show them shortly. So the exterior penalty method, it means that they're important for two reasons. They're simple and usually computationally efficient, as long as the constraint functions are fairly easy to handle, and we can easily detect an interior point of the problem. So if we know how to start from a nice point within this region, then, and the function that defines this boundary here, this feasible region, is to some extent at least nicely behaving, then we can deal with this problem of the constraint by using the exterior penalty method. So let's start with the first, a very rough situation, which it's not really applicable in practice. Usually, let's define a penalty function P as follows. Whenever x is smaller than or equal to 0, it's 0. And whenever x is positive, then it's infinite. So it's 0 elsewhere, and when we get to 0, it's still 0. But once we step to any positive number, it immediately jumps to infinity. Or if you are more comfortable with thinking this is something like a very, very large number that we know that, for instance, our cost function that we are minimizing never attains in any reasonable values. I mean, it could be some very huge number m, where m is larger than f of x in any feasible, I mean, in any foreseeable region near here. And we can consider the following problem, which is a free problem without any constraints. So we're minimizing g of x, where g of x is simply the cost function f of x plus a capital P of x, which is simply the sum of p over of g, the small p of gi of x. Meaning that what does it mean? It means that we are basically minimizing this f of x plus some penalty, and then this penalty is a function that is always 0 as long as all those gi of x's are negative or 0, but as soon as any of them is positive, then it immediately jumps to infinity. So obviously any minimum of this is found when this gi of x all are non-positive. Okay, seems easy enough. The problem, of course, is how to deal with a function that works like this, because, you know, its derivative, what is it? What does its derivative look like? I mean, what are we going to do? Where do we, what can we do with it? I mean, it doesn't have a derivative. We calculate the gradient inside the region, the gradient, the Hessian of everything of this g of x is completely unperturbed by this capital P of x, because it's simply 0. And if we are not exactly at 0, you know, with respect to any of these constraints, terminology, if none of the constraints are active at this point x, then this capital P of x has no effect. It has no effect and doesn't have a derivative other than 0. It contributes nothing to anything. So it's very hard to make use of this function P of x. So if the feasible set is not empty, then clearly this minimum cannot be outside the feasible set, and, you know, the minimum inside the set will be just f of x. And so if the original f of x has a minimum inside the feasible region, then it's clearly the problem's solution. The practice is, of course, problem because, you know, this p is not continuous and it's not differentiable. So there are two ways in which we can use this method basically to help us transform the constraint problem into an unconstrained problem, or the free problem. So one way is to use a different kind of exterior penalty called the quadratic penalty. So it's 0 elsewhere except when we are about to enter the forbidden zone, P of x starts growing quadratically. So basically what it means is that if we get into this infeasible region, then this penalty starts growing quadratically when we cross this border. The problem, of course, with this approach is then if we run a free problem algorithm, then we may end up optimizing to a point which is outside the feasible region just a little bit, because let's say that the actual optimum is on the edge here. Let me just draw the picture. Actual optimum is on the edge here, and this movement to outside the region is just very small, so that this g of x's don't grow all that big, and while the function still keeps diminishing, then we have a little room to go outside until this function is minimized, and the penalty is so big that it offsets any decrease in the function f. What is worse, if this g of x is so slowly growing function, for instance, let's say that our f of x is something like x to the 5, let's say, and we are moving to a negative x direction, and then this barrier function is of the x to the 2 or something like this, then, you know, not the barrier, the penalty function. The penalty function is x to the power of 2. Then the problem is that we can go infinitely long into the forbidden region, and it will not offset the whole problem at all. So here is the a problem. But let's say that this is not the problem. The g of x has this property that this is large enough to offset any movement eventually, at least of the actual cost function. Now, if we do this free problem and we invent a new penalty parameter r, which we have two basically criteria for this penalty parameter r. It has to be large enough so that, you know, immediately when you cross the barrier or, you know, cross the feasible region, the R is so big that it starts growing very quickly, so that it stops any algorithm from moving too far outside the feasible region. On the other hand, if it's very, very large, then this new cost function for this free problem is numerically problematic, because if f of x is derivatives and second derivatives, if you're dealing with Newton method, if it's Hessian and the gradients of it have components that are in the order of, you know, between 0 and 10 or something like this, let's say minus 10 and plus 10, and this R is 10 billion, then when you calculate the Hessian of this at or near the boundary, then it will look like the condition is very bad. The condition of those matrices are very bad. So it's numerically problematic because it's sensitive to small changes in that result, for instance, from rounding errors or use of a floating point arithmetic and so forth. So we run into problem of ill-conditioned problems. We say that it's numerically ill-conditioned if it's unreasonably sensitive to small perturbations of where we start from, or you know when we calculate these Hessians or whatever, then they are so close to being singular that from numerical point of view, we get results that are nonsensical. So this is a heuristic that we can apply on top of, I mean, we can this is like a wraparound algorithm for any free problem algorithm. So let's say that inside the engine, we are running a Newton method or a quasi-Newton method for minimizing a function. So what we do is we choose a penalty that is not too large. We minimize this theta function, which is now the penalty one that has the penalty function and the penalty parameter. And we come up with the solution x star, which will then depend on what this penalty parameter is. So in general, unless the actual solution is an interior point so that there are no active constraints, so that the penalty function is 0. I mean, it is possible that the optimum is inside the region and we're not anywhere near an edge. That's fine. But if the optimum point is like this, on the edge of the region, then usually the x star will be here outside the region. And the idea is that as R, I'm going to put it closer, is that as R grows, we solve it again and again and again, and we get closer and closer to this point on the edge, which is the actual solution of the problem. Here's an example. For example, choose RK plus 1 is 10 times RK, and go to step 2. And resolve it and so forth. So this is a way of minimizing it, and we can do this, and yeah, and the theorem that we give here tells us that under rather general conditions, this method, where we successively solve a free problem with the penalty increasing, tends to converge to a point on the edge that is an actual minimum. If the following set conditions are satisfied, the penalty function needs to be greater than or equal to 0, so it's non-negative. It never downplays the cost when we incur this penalty. It's 0 exactly when we are inside the region, and it's continuous. So it is continuous. It means that when we move a little bit outside 0, it's continuous, and let's say it's differentiable, but we're just saying continuous here because we don't take into account we don't take any, what do you say? We don't make any statement about what the algorithm is that is used to minimizing this modified problem, this theta, x, and r. Obviously, if we want to use a method that uses second derivatives, we want it to be continuously differentiable or twice differentiable. If we assume that this original cost function is continuous and the region is closed, and this cost function is such that if we go far enough in any direction, it goes to infinity. So that rules out, like the example which I said, if f of x is like contains a component like x to the 5, so that if we go to a negative x, it decreases heavily, and the penalty is unable to catch up to this. If there's no such problem, so that, you know, if we are in two-dimensional space, for example, it's just a graphical explanation. So if we go into any direction far enough, then the function will eventually start growing. So there's no direction into which we go, so that the function will start decreasing or remain the same at a very low level. And the penalty function, or one of these has to hold, or the region is bounded. It means that it doesn't extend to infinity anywhere, and the penalty goes to 0 the further we, not 0, it goes to infinity the further we go from the edge. Then if we have an increasing sequence of, if we keep increasing the penalty on this penalty method, then this sequence of points converges to an accumulation point, which is a global minimum of the constraint problem. An accumulation point meaning that it's an accumulation point of this sequence of points. So if we take this is, let's say, the first iteration leads there, the second there, and third there, and we keep doing infinitely, increasing the r, then the points get closer and closer to the point that is on the edge of the region, such that that point on the edge of the region is is an accumulation point of the sequence. You can say it's a limit of the sequence. We don't want to say it's a limit of the sequence here for some reason, but let's say that it's a limit. Think it's a limit of the sequence if you want, and each such accumulation point, or the limit of the sequence, is actually the global minimum of the constraint problem. So it does solve the problem. Only this is problematic from the point of view of talking numerics, because it doesn't say anything about how fast it converges. And we'll try around this. Don't worry. We'll try this and play around with this in the exercises, but we'll see that there are certain problems pertaining to this. So this is the external penalty method, meaning the name says it all. As you go outside the feasible region, you incur a penalty, and you just keep increasing the penalty until it forces the problem to be solved only at the edge or inside the region. The quadratic penalty function is continuously differentiable, but the problem is its Hessian is discontinuous at 0, so that means that the penalty function has a quadratic penalty function has a discontinuous derivative, and there's a problem with the Newton method or similar methods when we are dealing with exterior penalty methods. Here's an example fairly quickly. Let's go through this. So we should solve this with the external penalty method and use quadratic penalty function. I'm going to be using MATLAB here a little bit shortly. I'll do this, but let's first read this. So we are minimizing a simple x1 squared plus x2 squared subject to x1 times x2 must be greater than or equal to 1. So we can refresh this constraint as 1 minus x1 times x2, and that should be less than or equal to 0. So that this constraint here is expressed as g of x is 1 minus x1 times x2, which should be smaller than or equal to 0. If you calculate this, this penalty, we take the penalty function of x, which is the x squared. Its penalty, the small p, you know, this is now the penalty function's derivative is, because it's simply 0 when x is smaller than or equal to 0, and it's 2x squared when x is greater than 0. So its derivative is simply 0, 2x. So it's either 2 times the maximum of x and 0. If we minimize this penalty function, we're now going to be applying the penalty function on this g of x, right? And this penalty coefficient is this r. So our theta, the penalized function, is f of x plus r times the penalty of g of x. Penalty being 0 when x is negative and x squared when x is positive. So it amounts to x1 squared plus x2 squared plus r times the p of 1 minus x1 times x2. We can calculate its gradient using this derivative. The gradient is done thus. Actually, I'm not going to do the MATLAB thing now because I know how to do it, but I've forgotten what the function is. There is a function that does this step function, but I'm going to have to take a rain check because I don't remember what it is. I'll have to look into the manual, and I don't want to use the time of this lecture to do that. So we can calculate its gradient. We can set the gradient to 0 analytically. Obviously, if we are in an interior point, meaning that the constraints are satisfied, then the gradient is given by 2x1, 2x2, and setting it to 0, it means that the gradient is 0 at the origin. But the problem is that at the origin, this constraint is not satisfied. So the origin is not an interior point of this problem. So one way to check if it has an interior point solution is simply to disregard all the constraints. If the only constraints we have are inequality constraints. So we disregard all the constraints and calculate the gradient and set it to 0. In this case, we can do it analytically, and we find out that the solution is a point that doesn't satisfy the constraints. So it's infeasible. Now, if we assume that this penalty is positive, so we are going to have to violate the constraint, and we just see as a function of r how much do we violate it. And because of here, look here, we calculate the constraints so that this is discontinuous, but if we assume that we have to incur the penalty, then the gradient is given by 2rx2. I mean, here, we at a minus 2rx2 times 1 minus x1, x2. So this is what we get, and the similar with x1 in the second component here. So as long as we are outside the feasible region and we are incurring some penalty at least, then the gradient will look like this, and we set it to 0. So this solves it analytically. We don't have to do it numerically now. We'll do this in the exercises later, this numerical solution. Now, we set this gradient to 0, and we can solve this by solving that, substituting these in the equations. I'm not going to go into the detail. You can verify that if we solve this first equation, setting this to 0, move all that stuff into the right-hand side, divide by 2r, 2, and eliminate the 2 as a coefficient, and divide by x squared, sorry, x2. We get that 1 minus x1, x2 is equal to x1 divided by r, x2. Substitute this in the second equation here. That is the second line, putting this to 0. We get that x2 is plus or minus x1. So we have x2 is x1 or x2 is minus x1. So either the x1 and x2 are the same, or they are opposite. They have opposite values. So we have two possibilities. If we set them to be equal, then we can use this to solve this equation here. Set x1 equal to x2. So the first one becomes x1 minus r x1 times 1 minus x1 squared is equal to 0. And we get a solution for x with respect to r. So that x1 is plus or minus the square root of 1 minus 1 over r. And now we have a solution that depends on r. It's a closed form solution. In general, we don't get this, but in this situation, we get solution that depends on r. We know that x is plus or minus, x1 is plus or minus x2. So in this situation, if we let r approach infinity, then this approaches plus or minus 1, and x2 will be equal to that. We are only interested in situations where this r is very large and it approaches infinity. And solving for this, you know, this is calculating the first equation and the second equation. If we get x2 is equal to minus x1, then we get an impossible situation. This expression here is positive. So this is positive, and x1 was not equal to 0, so it cannot be 0. So obviously this is infeasible. So the points that we get when r is going to approach infinity would be points 1, 1 and minus 1, minus 1. All right. Here are some examples in which it uses examples that use a slightly different version of the penalty functions. I'm not going to go in this problem. I mean, one way to do this is to just have this is like adding a slack variable. This is like adding a slack variable here. So it's to what extent are we breaking the or, you know, not breaking, or to what extent are we outside the region, and then solving it. Well, in fact, in this case, U1 would be G1 plus U1. So yeah, this is to what extent are we inside the region, right? We calculate the penalty for that, then we can solve it. I'm not going to go in detail in this. This example can be, there are various ways in which we can transform these inequality constraint into equality constraints. Not going to go into that in detail here. Here's another situation, is the so-called augmented Lagrangian method. Not going to go in detail in here. I mean, this is again possible thing that we can do for the modeling exercise, or the exercise, or the project work, or, you know, something if you want to work on this. I'm not going to talk about the augmented Lagrangian. You know that it exists, so it's kind of based on the idea of doing the Lagrange function, or the Lagrange method, using the Lagrange method in a way in which we we transform the inequality constraint into an equality constraint, and then we augment the Lagrange function. I mean, here would be the usual Lagrangian, right? But here's a quadratic term here that has the penalized function, so that we want this to be as small as possible. And then we can just do the Lagrange method, and we can find the KKT points of the original problem. The idea of these external penalty methods, then, you know, it's one of two ways. One, we just directly apply the penalty when we are outside the region. We discussed that a little bit more. Or two, you use a penalty function to augment the function into an equality constraint, and then, you know, you use the Lagrange method to do that, to solve that. The barrier function method, on the other hand, works in a different way. In this case, the interior points, well, obviously this works only when the set of interior points is there are interior points which contain there are feasible interior points. This means that there are points that are inside the region and there's room to maneuver around them. And the boundary point is an accumulation point of the set of interior points, so that there are no outside points that are not, no boundary points somewhere that are not actually accumulation points of this region. So there's not isolated points that could be the optimum. So really, I mean, intuitively, the region looks something like this. And one way to do this is to find an interior point, and instead of giving a penalty for going outside the region, give a penalty that increases when you approach, when you get too close to the border of the region from within. So come up with a function that if you are going to approach the border, then very close to the border, it jumps to infinity, so that the cost function, when we're minimizing, it's negligible, the barrier here, but once we get closer, the barrier rises, and we get close to the edge here, but not quite not quite reaching the edge, because there's a barrier, a function that is preventing us. The cost is too great, of crossing the barrier. Here is a function definition. It's a barrier if it means that the barrier function of x approaches infinity as x approaches a boundary point of the region. So when we are approaching this region boundary here, right here, then it approaches infinity. I mean, in practice, if g of x must be smaller than or equal to 0, then it must approach infinity as g of x approaches, as x approaches 0, sorry, as g of x approaches 0 from the negative side. So here are examples of barrier methods. I mean, we can have this barrier method. We can take the logarithm of the absolute value of g. We can take the negative of the 1 over g. Obviously, both of these are functions that go to infinity as g of x approaches 0 from the negative side. And we can replace the original problem now, take the original cost function, but now we incur this barrier with a coefficient t. And in this case, we've raised the barrier. So you can think of it in such a way that usually we have this, we have this region where there's a sharp edge, but now we kind of raise the edges, of the region and prevent algorithms from, converging outside the region, because when we approach the edge, the cost increases rapidly towards infinity when we get too close to the edge. And this is a really nice result. this T here, that can be thought of as the parameter for the barrier of how steeply it increases. Obviously, when we get close enough, it goes to infinity. So it's very steep near the barrier, but how far from the barrier does it increase in steepness? If T is very big, then we can't get very close to the edge of the region before the barrier increases. But if T is very, very small, then as long as we don't get too close to the barrier, to the edge, the barrier doesn't rise. So there are some drawbacks. The barrier parameter now has an opposite problem to the penalty parameter. I mean, we had the penalty parameter, which was the R times something, and then R has to increase, and it becomes numerically problematic when R is very big. But here, the barrier parameter T should go down. So when it gets very close to zero, then again, we have a similar problem that the barriers coefficient is so small that the algorithms all but ignore it when we are far from the edge, and then they may accidentally jump over the edge or cause problems. And the Hessian becomes ill-conditioned because the Hessian has now one parameter that has a problematic behavior. We'll see that. We'll discuss this, and we can these are fairly easy to implement in MATLAB. So I mean, we can come up with a barrier function, just add the penalty, and then solve it as we would, and then just add one loop around the algorithm in which we, in the barrier method case, we decrease the barrier. In the external penalty method, we increase the R. So we can try both. Here's an example again. This is done analytically. There are two constraints, which now are linear constraints or affine constraints. Here's an example. It's done pretty much analytically, and we get this barrier parameter T appear here. And when the barrier parameter T appears here, and when T approaches zero, then what happens is that we get a solution that is converges as T approaches zero. It converges towards the feasible solution 1 and 0. The problem is if we look at the Hessian here, here's the Hessian in this particular case, as T goes to as T goes to 0, the Hessian's condition number tends to infinity. And there is a problem there. And, we have to figure out a way to overcome this. So there is a problem there. All right. Now, I'm going to skip the ellipsoid method here. I mean, I haven't updated this. I'm going to skip the ellipsoid method. I'm going to just explain quickly what it is. But the idea here is that we approximate a convex region by an ellipsoid. So basically an ellipsoid is a generalization of a ball. So instead of having the quadratic form, just directly, x1, x minus a squared plus y minus b squared plus z minus c squared smaller than or equal to r squared. This would result in an r radius sphere centered at the coordinates a, b, c, right? But we can generalize this into a general quadratic form, which can then squeeze and rotate this. We call it an ellipsoid. You can think of this if it's two-dimensional, you can think of the quadratic form as being an ellipse. As long as this Q is a symmetric positive definite matrix, then this form will result in a ellipsoid that is centered at x0. The scaling of the matrix is used to indicate the radiuses, the radii of the ellipsoid, and this 1 is just a single parameter. It doesn't really matter what this parameter is, because if this is different, then we can just multiply this with a constant and get this. So the ellipsoid method in this constraint optimization works in a way that we assume that our optimum point is inside this ellipsoid somewhere. And the algorithm behaves in a way that makes sure that the optimum is contained in the ellipsoid at all times. We make the ellipsoid smaller and smaller based on what we know about the point and the parameters. I'm not going to go into details here. We compute a new center for it, and we squeeze the ellipsoid until such a time as it's squeezed into a single small, so small an ellipsoid that it's just, for all intents and purposes, contains to a great accuracy our point, and we're done. So I'm not going to go into the details here, but the methods here are such that they guarantee, and there's a proof here as well, which we don't discuss now. All right. So next come the problems, and that there's one problem here, but I'm going to invent new problems for you guys. So basically what we're now done with the methods in this slides. So the rest of the course we will practice with MATLAB, and we'll get back to these theories whenever we see some problem that we need to solve. Right? So the rest of this course, we will be solving these problems that we have on the internet, on the Moodle page, and I'm going to show you how to do that. And for the lectures, we will be also doing this practical work now. So the theoretical part is pretty much here. We will, of course, return to these matters next week when need be, but mostly we will discuss examples here. So I'm sorry it took a few minutes more time than I had planned, but I wanted to get this finished and so forth. There is one additional theoretical content that will be, it's not in this constraint optimization theme, it's the extended cutting plane method, which I will explain next week. It's not in this material, but the slides are there on Moodle. And the idea of that is somewhat different from these methods. I mean, for the constraint optimization, the extended cutting plane method works by taking unconstrained, getting rid of the constraints, solving a problem, then looking at what constraints are violated, then coming up with just a linear constraint that says that, okay, this is where we violated it, we want this side of the region, and that side we can forget. And then we do it again and again, and eventually we come up with a polygon that contains the original problem and the solution. So we're successively basically solving either unconstrained, or I'll show you, we can even solve only linear LP problems and eventually converge into a optimum solution of the whole problem. So I'll show you that next week. But this slide thing, this is done now. All right. Sorry for going a bit over time. I hope you enjoyed this lecture. If you have any questions now, let me know.
Onko siellä Moodlessa tapahtunut